Alright, time for another draft science video presentation. Such. Hope to do a video response somewhere in this video to this Maxwell's equations visualized. So this is like a real big problem in physics, is the Piro syndrome, where it seems like it is like. So, the scientists really haven't figured out that because something looks like something doesn't mean it is something. And I shouldn't say the scientists, I probably should say reckless and stupid thinkers haven't figured out that you gotta be careful about that kind of stuff, because that's the biggest mistake you can make, is to do this book by its cover kind of thing, and not realize your senses can be fooled and all of that crap. So someone's commenting on Ken Wheeler's ferrocell, and mostly, and it relates to the Maxwell thing in terms of not making distinctions between, what the math really is, if you were to visualize it, what it's saying, and the good parts of the math anyway, and and what the what people think with magnets and these lines with arrows on them, they're just so dangerous. But it looks like something, but what you're seeing isn't. It's a composite of other information, and it isn't as it seems, in the sense that nothing's moving from one end to the other end. There's no evidence of any of that and all that stuff, and there's no evidence that photons can be bent by magnetism. And clearly what you're seeing in ferrocells is an illusion created by a circumstance that you're not understanding, a mechanism, an underlying mechanism. And I'd say the same is true for the two-slit experiment and all of that, in that there's an underlying mechanism that's creating the pattern, and physics doesn't really want to pay any attention to underlying mechanisms, like, the matter of the slit. So anyway, maybe I'll throw a drawing in as necessary. I love how this is stream. I don't really like that word stream. Explains way more about actual physics than all the guy that's getting roasted videos, probably a comma, videos ever released combined. Well, it's still not got a good sentence. If you want to have a laugh, look, I write plenty of bad sentences, I'm just saying. If you want to have a laugh, look at his PDF version on magnetism. It's I already done videos on it. It's basically an online, available for free. Well, he's trying to sell it, but he also provides a free copy. But anyway, it's filled with nonsense from start to finish. It's filled with quotes, not explanations. Probably a waste of time to even bother. Yes, of course it is. But geesh, it's also ironic how he insists that Tesla is somehow a genius. Well, obviously he had his moments, with Einstein being a moron, which is kind of stupid. Einstein was a pretty smart fellow, but completely wrong about a lot of stuff. I think he knew he was wrong. I mean, that's why he was he ended up being, the advocate against a lot of his own concept, in a sense, later in life. Other people were preaching, but Einstein says, to Einstein, and Einstein was like, no, not exactly. Anyway, somehow that doesn't add up. He has also made sure the first couple of pages are filled with advertisements for stuff he sells or is affiliated with. It's pretty easy to see the guy is a scammer. I think the scam is, it's pretty easy to see that the guy is an egomaniacal kook. That's what's pretty easy to see. And it's filled with quotes like, beware of false knowledge, it's more dangerous than ignorance. Well, obviously, believing nothing, going, I don't know, is less dangerous in most cases than some asshole who says, I'm a very good driver. So it's true, okay, that false confidence is worse, okay, than ignorance. Reminding us a lot about the psychology of a lot of New Age stuff relies on. It is clearly psychology, is clearly not It doesn't. None of these conversations about vacuum energy and all this other crapola, free energy or whatever they call it, non something or other. It's just, it's a psychological problem. It's not a problem of logic because they're not really applying logic. There's something cult-like about it all. There's something cult-like about the whole human race, clearly. They've been like that for a long time. They're very groupy animals. And that's disturbing. There are an awful lot of sheeple following wildebeest. I mean, the sheeple don't even really understand what they're following. That's how funny it is. The creature they're electing or the creature they're idolizing is a creature, that isn't even the same species as they are. Definitely all BS. Videos like this are underrated. Well, I would agree that the dumbasses are really missing out on being called a dumbass. Anyway, people like this Wheeler need to be exposed. Yes, they need for the people, the sheeple, to understand simple concepts like, well, gee, that guy has challenged him to a debate 468,000 times, and he's not debated him. What is he, afraid to entertain us by showing how much smarter he is than everybody else? Why won't he debate anybody? Yeah, maybe they should figure out at least that much, the stupid cowards. Alright, too many people fall for this big words that actually make no sense. Well, they certainly don't in the context that he's using them. Not saying the words should be shot, but yes, the words don't offend logic. People do, kind of thing. Brains gone bad. Alright, and then flux aspect engineering. It's actually a code. It's against the code of ethics for me to say if something is a scammer or not. Well, I don't know why that would be. So, what? If somebody's getting raped, you won't say, "Hey, there's rape happening." But we can say if they are wrong. Well, I think scamming is a kind of a wrong. So, gee. And the guy who is pissing off a revolutionary new type of passing off a new type of ferromagnetic fluid heel saw cell has anything more than a poorly assembled variant is something wrong. So he's passing off this ferro cell as something more than. I would say it is something more than, so I think that's just, you're exaggerating. The guy who figured out this thing he did something. He figured out different light sources. If you put them all together, you can make this spirograph pattern, and it looks pretty. So the fact that maybe in 1940 they knew that you could create a curved line doesn't mean the guy who put all the curved lines together doesn't deserve whatever. I mean, it is pretty. It's a nice little toy, but it's just that. So anyway, that's the guy who left the long comment on the ferrocell, I guess, and I'm really just not going through the whole history of that kind of crap, and maybe on a different video when ferrocells come up I will explain again, but I don't think his own understanding of light is anywhere near coherent, so what's the point? So superior mind. I'm now wondering about reflections, and that this is where it all ties together. So this is about reflections. It is about how energy goes into things and how it comes out. And what I've basically discovered is that whether you transmit the energy or whether you reflect the energy, a mirror, a shiny surface, or whether you, what's the third choice, absorb the energy, it's all exactly the same in terms of they're all reflections. It's just you can't see the reflection. See, when light bounces off of something and reflects, it reflects into our eye, but we don't see what happens to the source. So the real truth is that when it's reflected, the equal and opposite reaction is essentially swimmers going the opposite way. So for every light beam that hits the surface, the photons go right back, and they go back to the source though. And we're never the source. We don't shoot rays to see something. We see rays from some other angle. They go back the way they came. And you can sort of see this in a laser experiment with the old MIT doing versions of the single slit experiment, and they actually catch the light going back to the source. It's always going back to the source, ironically, in fact. So something you think is an absorption is really a reflection. You just didn't see the reflection because either the photons were broken, that is, half the photon went one way and half the photon went another way, and you can't see tiny bits of ray, or it went back in a direction that isn't into your eye, so you're not going to see it. You weren't the source of the light. Obviously, the photons that are reflecting back to you, the ones that reflect to you, came from some other direction, and that's where the reflection goes. So you obviously can't see light you didn't produce. Anyway, your eyeball didn't produce. And it's really, it's all very simple, but the nuance of it is just, deep. Anyway, so bear in mind, I'm now wondering about reflections, in that if something could be engineered like some nanotech material to reflect an extremely wide range of frequencies. Again, this materials already exist. Stuff reflects lots of materials reflect lots of kind of stuff and absorb different stuff and transmit different stuff. So glass is opaque to a lot of frequencies, even though it's transparent to the visible frequencies. How much effect would it have on an object being accelerated by radiation in space? So this is another interesting point, in the sense that when you have one of those, what do they call them? The little thing with the triangles, okay, a little spinning in the globe. And the truth was found that in a perfect, the stronger you make the vacuum, nothing happens. It doesn't spin anymore. That it actually needs the atmospheric atoms to be able to catch the energy that's reflecting, and to catch it in a way where they reflect it back to the surface to cause the pressure that moves it. So it's not moving based on the light that hits it. It's moving based on the fact that the light reflects back and forth, like I've tried to explain before. So if the radiation is in the right form, it reflects off the atoms that are still left in the globe, and on one side it's in a form that doesn't reflect, that gets transmitted. I'm stepping up a little too far. I don't want to get into those mechanics, but the point is, it doesn't reflect it back at the same angle, so you can't create the reflection. See, if it comes right back to the source in one piece, then it gets caught, and it can go back and forth and create pressure. If it comes back as an angle, then it doesn't stay. It doesn't create a constant pressure. But anyway, I don't want to get into that. The simple point is that in a pure vacuum, the thing doesn't spin. The black side and the white side are the same, the shiny side. There's no difference in the pressure. So fundamentally, they're both doing the same thing. In the sense they're getting hit by photons. They're both moving, and they're both moving in the same direction, which means they can't move, this way and that way. They can't spin. It sort of proves the point, is what I'm saying, is the more vacuum you have, the less movement you have, which sort of demonstrates it doesn't matter whether the surface looks black or whether the surface looks like a mirror. It's all creating the same momentum in the material, and the momentum will be realized in a different outcome, in the sense that you might see what's transmitted, you might get hot, so you'll transmit it, or you'll heat up, you'll do something, but the energy doesn't disappear, but the energy always has a reflective component. What happens to it after it's in the object is another story. So there's two components. There's the first component where, force A jumps into the electron boat, and force B comes out in the opposite direction. That's one action. The other action is now the boat's moving. And that boat inevitably can do exactly the same thing in some other direction where it lets, rower A back out and it collects some other rower C. So there'll be another action. So each action has two components: the in interaction and the out interaction. All right. That's probably more than I wanted to say. So just quickly before we get on to the, well, I should see if there's more comments. One more. Age of Reason. You can't do this to me. It's 4 a.m. I was about to go to bed when this popped up. I didn't even know you had this channel. Well, then you don't pay very good attention, frankly. Looking forward to listening to more. I mean, I did originally do these videos on the Amendum channel, and I made a new channel just because people were pissed off that I was doing physics on the Amendum channel. But anyway, it doesn't matter. Enjoy yourself, or something like that. So let's understand the point being made here is, the general point is that people say they're looking at something and saying, okay, there's a phenomenon. So we have the single slit thing, and whoops, boy, I really gotta get my bearings. And we put plane photons. Gee, what the hell is wrong with this? I can't orient my hand. Nothing. Anyway, we put plane photons in, and we get some sort of stupid ass thing happens, a magical breaking of the photons, and wait, we get this back out. We get this bars, and so we're seeing something, and it seems like, well, it's sort of like when water does this, but obviously it's nothing to break the wave in two, and there's no interference, and blah 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 in the single slit. So the point I'm making is the obvious thing to blame is this material here as being the agent. All right, now the ferrocell does something a little different in the sense that you shine a light in from a direction, and it creates this little funny line. Okay. Something like that, I think. Yeah, I think so. Anyway, and so then if you put a light source here and a light source here, you can understand it'll do this, and then this, and then, get this little pattern in there. Okay, if you have all these little different sources, for every source you'll have a new little line. Now, the photons aren't creating this bent line, and the magnet isn't, right? And the magnet... Make sure. Sorry, I really have to tighten up my presentation performance skill thing set, blah blah blah. Oh, look at that. So what's really the magnet is here, right? So we're seeing all these funky lines, and people are thinking, oh, look at all that weird stuff, and the fields are complex and all. Now what the magnetic filings are doing is lining up in this way. Okay, the magnets are this way. Okay, lining up this way, just like they're supposed to, and they have the same magnetic field. That is, they're all oriented, let's say, plus to minus, or north to south, and so all of these lines end up being repulsive to each other because they're the same magnet essentially. So they create a bunch of actual lines of ferro material, where the little ferro bits are all stuck to each other and they're pointing in that direction. The ferro bits are longer than they are fat, so they have a little north end and a little south end. And so that's all that the material's actually doing. And so when the light comes in, what it's doing is it's reflecting off of this bit, and then it reflects off this bit, and it reflects off this bit, and it reflects off this bit. So that's how the curved line is being created. A little bit of the light's reflecting off each one of these lines, instead of what you would expect, which is it reflects off this line, or it reflects off this line. Well, no, each photon hits a different one because of the angle, and so each one is hitting a different line, and so that's how the line looks curved, but it's not really curved. There's nothing curved. There's no curved field. There's no curved influence. It's completely an illusion, the curve. Doesn't have anything to do with anything mechanical. Everything mechanical is in very straight lines. Alright. So off to the idiot. The asshole, the jerk, the fool, the whatever. You know, he does look a little bit like, you know, he's got like the Jack Nicholson after the lobotomy in Cuckoo's Nest. But anyway, we're not supposed to do the look-like thing. Yeah, never mind. He seems like an asshole. Sometimes, when something seems like something, it is something. That's the catch. Some stupid commercial note.
How big should a drone battery be to maximize its time spent in the air? In order to fly, a drone needs energy. But if the battery's too big, the energy is wasted carrying it.
Hey, crazies. Sometimes math is unavoidable.
So, I don't know what it is. Hey, crazies. I mean, that appeals to people. Math is unavoidable, yes. I don't know if it's ever really. I mean, you can always reduce math to a pile of something. You know, when you say, you know, here's two things over here, and here's two things over here. And then you can explain how, see, if I push them together, they're four things. Well, I almost made them three. They're four things. Yeah. So you could do it with blocks. You could do them with images. So I think all equations could, if you really wanted to go to the trouble, you could take each quantity and make it into a thing, a physical thing, and then you could show how, what division and multiplication are. You know, that you have sets of things and that you're splitting the sets up into 6 parts or splitting the set. You know, you could do all that visually.
Without it, you miss out on important insights.
I doubt that. I completely doubt that. It isn't insightful. It's such an abstraction. It's not the real thing. I mean, it's really not a manipulation of the thing in front of you. It's like a magic trick. The little lines, the little divisions, the little multiplications don't really explain what's happening. They don't give you any visual clue.
So what if, instead of avoiding math, we try to visualize it?
There you go. So, see? It's not really the same thing then. But okay, let's play along.
I want to give you a glimpse inside my head for a few minutes.
Alright, so here they are showing this simulation. And they actually have what are the iron filings, which look just like iron filings. And they're showing them moving in this funny way. They don't do any of that. So if you actually saw Maxwell's equations, you see these little orange arrows? I mean, that's how Maxwell represents the math. So if you convert this into a charge, just call this the electron and call this the proton. What Maxwell would say is, yes, one kind of energy is the opposite of the other kind. So you just have out arrows for the one kind and you have in arrows for the other kind. And then you just measure the intensity, the distance, will tell you how big that arrow is. So how big the out arrow is and how big the in arrow is. It just goes based on distance. So the further away you are, the smaller the little arrow would be. And if you measure those two influences, that'll tell you what angle the thing is at. So if it's right in between, it'll be a nice straight parallel arrow. But if it's a little forward this way, well then it's going to bend a little bit more towards the south end, a little less towards the end because of the propulsion, and it's going to start bending. And you know, and it's that simple really. So the real drawings are straight lines. The real lines of force, as Maxwell would describe them, are straight lines, and you're basically just spacing the lines, having them diverge at a specific rate to define what field you're in, whether it's a dipole field or a monopole field or a field of unequal sizes. So, and that's all you're doing. And so then when you put two things in proximity, you're just counting, well, how many lines radiating from this does this object intersect? And you can sort of understand, the closer I am to it, the more of the lines that will hit me. The further away I am, all these lines miss, right? You can get that, right? There's a whole bunch of lines coming off rays, and the further away I am, the less of those lines I'm going to intersect. And that's the math. None of this happens. None of this movement happens. The arrows just represent direction. It just represents what direction will an electron move. And if I switch it to a proton, it's what direction with the proton move. I just reverse all the arrows. And that's it. There's no actual movement from north to south. It's just the direction a negative charge would move or a positive charge would move. So, fake simulation to start the video. Thank you.
This episode was made possible by generous supporters on Patreon.
Assholes who waste their money on assholes.
Okay, so the math I want to help you visualize today is divergence and curl. But this isn't a math channel. It's a science channel. We need context.
Yeah, I'm sorry. You don't do any of either one. Well, reasonably.
Fluid flow seems like an obvious choice, but those aren't always simple.
Yes, well, Einstein's math gets converted into a fluid dynamics, right? So this whole lie of a bent space, when they're really talking about a well that water falls down. Well, space, everybody should know, isn't water, and it doesn't fall into wells.
Sometimes they're rather complicated. And if we're being honest, I don't really understand fluid mechanics as much as I'd like to. I'm trying to teach myself, but that takes time. So
what's your excuse then? So you're just going to do more of the generic crap that has left people with a wrong impression about how things actually function. And you're going to do it, like I said, so overtly, where you're going to take those little arrows seriously and say somehow we've measured an actual current in that direction, an actual flow, an actual stream, and that you could throw confetti in it and you could watch the confetti move. It will not move. You throw the iron filings around the magnet and they do not go move from the south end to the north end or do any. Nothing moves that way. Nothing.
We'll reserve fluid animations like this for analogies only. Let's focus on...
So again, they're not analogous, just as the water example isn't analogous to what light does in a single slit, and certainly isn't analogous to what light does through a diffraction gradient. And it's not even analogous to what light does in the double slit, because light creates the complex pattern of two patterns molded into each other, and water doesn't. So again, these analogies fail as description. You're not really explaining it because the two things don't match enough.
On something I happen to know a lot about, the electromagnetic field, which is...
Oh, what a joke. You have no clue.
It's actually a combination of...
Yes, right. It's two fields of fieldiness. A field of what? Virtual photons. So you understand virtual photons really well. I mean, amazing crap.
Two different fields.
Yeah, there's no two different fields. So again, all there is the fields created by charge. You have individual charges. They're called monopoles. You put the two right next to each other and you have something called a dipole. And the dipole is a magnet. And another magnet can detect the orientation of another magnet because it's producing more, whatever you want to say, electron force at one end and proton force at the other is reflecting more. And they detect each other's fields. In the sense they detect each other's radiation, pressure. And I've explained this. It's all about the reflection thing.
Electric field, shown in blue, and a magnetic field, shown in orange. We did a whole series.
So, yes, and they're all wrong. They're all bad physics. And they're probably, again, do the same thing. Look, the magnetic, the lines of the stuff are lined up. They're not lined up for any other reason than they're the same magnetic orientation, which is repulsive. Like magnets repel like magnet orientation. So that's why the iron filings are in lines. And the lines don't really have any movement in any direction. They just have an orientation. That is, one side is going to influence electrons in a certain way, and the other side will affect the electron the opposite way. One side will be repulsive to an electron, one side will be attractive to an electron. That's all the arrows represent.
On how we discovered those fields and what they do, but I didn't talk about divergence and curl at all, and I think that was a
So yeah, and I don't think saying visualizing Maxwell's equations, frankly, is curl and divergence. But anyway, let's go.
mistake. So it's time to fix it. We have two behaviors, divergence and curl, acting on two different fields, electric and magnetic.
So there's divergence. Curl is sort of bullshit. It's an emergent property. All there really is the divergence of a straight line radial force. And there are no two fields. There's just the charge field. You want to call it charge, you want to call it magnet. Doesn't really matter. The north-south is essentially a representation of electron dense and proton dense. And the proton and the electron are essentially the magnetic monopoles, but there's only one kind of field. It either has a lot of red in it or black in it. You know, so that's all you're changing. So if you think of the electron force as red and the proton force, the reflective force as blue, then all you're doing when you're looking at a magnet is saying you're mixing the two a little bit more, but they still have a polar end. One end is more blue than the other end is red. You know, that's it.
That means we need four equations. They look something like this, the Maxwell Heaviside equations, which most people just call Maxwell's equation.
Right. Well, this is the stupidest one, right? This isn't an equation. There's no magnetic monopoles. That's not an equation. That's a statement. And it's, on its face, kind of stupid. Clearly, electrons and protons are the magnetic monopoles.
Don't get me started. But these constants are just there to make the units work out.
Right, so exactly. There is no, it's silly to even call them constants. They were never measured. The permeability of space and the permutivity of space, these were never measured quantities. They're not real things, and now they've even changed their names to the electric constant and the magnetic constant. So, you know, and why there would be two of them is kind of silly. Permutivity and permeability, I mean, you know, whatever, and they come out to be complete reciprocal, essentially, of the speed of light.
They're not actually important for understanding the equations, so I'll just set them all equal to 1. I do what I want. Alright, as we go through these one at a time, we'll look at the equation first, and then we'll see what we can do about making it more visual. Let's start with this one, also known as Gauss's law. It says the divergence of the electric field at some point equals the charge density at that same point.
Right, so all you're saying is that if I'm creating these radial lines, so I have a charge of 1. Now, to just illustrate, I can make 1,000,000 lines. That might be the truth, but yeah, I could just illustrate it with 10 lines spaced at a different distance. Now, if I if I double the density of the charge, that is, I put the two charges right on top of each other, right, morph them into each other, you can understand that now there's 20 lines, right? Or if I say the charge is a 2, not a 1, you know, it's a double charge, then there's twice as many lines. So there's twice as many lines coming out, so you're going to intersect twice as many lines at your destination. And the only thing that changes is you have to understand there's spheres, and spheres have 3 dimensions, and then you get into the inverse square law. But anyway.
In other words, the reason the electric field isn't just 0 everywhere is because electric charge exists. But this law tells us something.
So electric charge, it just should be called charge. The fact that electric is really just a phenomenon of atoms. So they really should change this language just to recognize that atoms move electricity. So there is no electrical thing until you start affecting atoms. That is, you make the atoms polar by moving the electrons further away from the proton or closer to the proton. You change the profile at a distance, what somebody sees when they look at it. If I move the Earth close to the sun, you as an observer could see the entire sun blocked out, right? I mean, technically. And it would look like, oh, space is just Earth. You know, I make the Earth further away, and then I make it further away from you, in terms of, and change the distance to the sun, then the sun can look huge and the Earth can look tiny. So it's all perspective.
About the shape of the field, too. Say we draw an imaginary sphere around some region of space. The outer surface of that sphere has electric field arrows sticking in or out of it.
So again, the arrows are just a representation of which way a charge would move. So in this case, you're using a charge the same as the little red dot. And so it's running away from the red dot and it's running towards the positive dot. So he didn't even explain that those two dots are, one's a positive charge, one's a negative charge. But there's no flow. It just depends on whether you're a positive charge or a negative charge. The arrows are completely reversed, and the arrows just have to do with, if you set a free thing in this space, where would it move, based on the force. But the force isn't, the force is radial and it's not curving. So the force doesn't curve. So this is just like the ferrocell in the sense that this is an illusion. None of the forces are moving in crooked lines. They're all just rays. And what they're doing where the lines are crooked is they're combining the effect of the pink dot and then combining it with the effect of the red dot and giving you the answer of the two forces effect. The pulling force from one end and the pushing force from the other end. And they're giving you the sum of that. And they're showing you what the sum looks like. But there is no sum in the actual field. Neither one of these things are producing the sum. And the sum can only be felt by something material. The sum can only, forces are only summed when you put something in the field. You can't sum them, you can't add them till you put something there. Whether it's a positive charge or a negative charge, something. You have to put a test charge in. Without the test charge, there's no curves at all. So I'm just saying they're all just forces that are straight line forces. And that's how Maxwell drew them. So why don't you just use those drawings?
Since that sphere is imaginary, we could make it any size we'd like. But to find the divergence, we need to make that sphere really small. Like, just a bit larger.
Right, so they're just making a test charge. Yeah.
Than the size of a single point, kind of small. You're such a little adorable sphere.
So this is, why, I don't even know how people watch this queer stuff.
Yes, you are. Yes, you are. Anyway, the divergence of a field tells us how much that field points away from that tiny sphere. If the field points into the sphere as much as it points out, then the divergence is zero. Gauss's law tells us there's no charge at that point. If the field...
So you're just saying the two charges are equal, would be the same thing as saying there's no charge, right? But that's not correct. So at the point where I go between the Earth and the Moon, there's a point where there's no gravity. No, what we should technically say, where there's no effect of gravity, where the two forces cancel each other out. There's plenty of gravity in the sense the Earth is creating those lines, the Moon is creating those lines. If the Earth wasn't there, the thing would be zooming towards the Moon. If the Moon wasn't there, the thing would be zooming towards the Earth. The point is that there's not that there's no gravity, there's no effect of gravity. It has no consequence at that location because the two forces destructively interfere, if you want to say, and cancel each other out. One pulls, one pushes an equal amount. Well, one pulls and one pulls an equal amount, if you want to say it that way. Or one pushes and one pushes an equal amount.
Points more out of that sphere than in, the divergence is a positive number. Gauss's law tells us there's positive charge at that.
Right, so all this is indicating, again, is that you're just testing for which way the field is. What side is proton, what side is electron? And I can test it with a proton or I can test it with an electron. And I'll find out which one is which. And then I'm just putting a plus and minus sign on them. And so I'm just turning now direction into plus and minus. But no, the direction really is just right to left or left to right based on what charge I put in. If I change the charge, I change the direction. It's just, it has nothing to do with the reality.
If the field points more into the sphere than out, the divergence is a negative number. Gauss's law tells us there's a negative charge.
So it just means the adding of the two effects. So the moon is over here, the earth is over here. You're just adding the two effects, which the two poles. So you're far away from the earth, so the arrows have gotten very short. You're close to the moon, but the arrows started shorter. And it just means the two arrows are the same size. That's all. The two objects are creating equal and opposite force.
At that point. Electric charge is the reason the field looks like that. Of course, that's all very static and...
No, that's all very useless. The electric force is the reason the field looks like that. That's not saying or explaining anything.
A little boring. If it helps, you can imagine this electric field is the velocity field for some fluid instead.
Yeah, see, now this is just a huge mistake. Some fluid, well, would have to be negative fluid, and if I change it to positive fluid, then it would move exactly the opposite direction. So again, this is just oriented towards the fact that most effects are electron effects. So most of these things are drawn in the traditional sense, in the sense that what you're really influencing is always electrons. So it has an obvious electron bias built into it, because electrons do all the action. The electrons on the outside of the atom, they do all the interacting with the outside world, essentially, and they do all the substantial moving. That is, they change their position relative to the proton. So they're the player. That's why it's traditionally drawn in one way, and the fluid moves one way, but it's no movement taking place. That's only telling you how the field averages. So, I mean, I've done this before. This is, it's done in Professor Lewin videos even. So this is the Maxwell starting point. This is, I think, Faraday's starting point. The object is radiating a force. With distance, these lines get further and further apart, essentially saying that the arrow starts off long, and the further away it goes, the arrow gets weaker and weaker. Okay? I mean, you can sort of get that idea. All right. Now, the field lines, the lines they're putting here, moving and bending, yeah, these lines bend, okay? But these lines are just representing what's the charge here? What's the product arrow? What's the product arrow look like if I have two things here? So this one's creating these rays. This one's creating these rays. I mix the rays and I say, well, if I'm here, how many rays am I getting hit by from this direction? And it's supersymmetry. They supersymmetry. No, it's oh, what's that? That stupid word is always escaping me. Superposition. Okay. The force doesn't interact with the force. You have to have an object here to say what's the force from this one, and you have to have an object here to say what the force from this one is, and you're just averaging them. So you're just saying that where is the force, in a certain, like if you actually put something there, which way would it move? Well, if these were both positive things, it would move that way, obviously, right? And if the one was positive, one was negative, then it would move this way, or So that's all that arrow represents, and it's just telling you an intensity. That is, the line is just a representation that it's all the same strength in all these locations. So it's like a topographical map in a sense, it's kind of better. But so on the magnet, this crap they draw of these lines, these are not real lines. Depending on what kind of material I put in, the lines will be in different locations. But as pointed out, these lines are just made of magnets. So the magnets all line up plus to minus, and so this one started off minus to plus, so they line up opposite because that's how they flip, right? I mean, if I have minus to minus, they're going to be repulsive, and the thing shoots away. So to line up, it has to have the same orientation, the opposite orientation of the magnet itself, so they flip based on the amount of pressure. So the pressure here, if I'm a minus, this pressure increases, it doubles because I start reflecting back and forth, and this is plus and plus, then I start reflecting back and forth, and I create more pressure, and the thing pushes away. And so the magnets line up the opposite way. They would, if they could, go right into the magnet. The only thing stopping them is the piece of paper that you've put in the way. So they would go right into the magnet. So they're stuck, and they're lining up the same orientation. So each one of these lines has the same orientation. So these lines are repulsive to each other. That's why there's a space between them. But that's it. It's completely arbitrary. It's emergent. There's no fundamental force here. These are the force. The force is rays. Rays of two different colors. The dotted lines maybe. So I don't feel like getting a color out, but it's all coming out blue here, and it's all coming out red here if you can get it. And the magnets are just lining up to their preference, which is their red end wants to go to the blue end, and their blue end wants to go to the red end. But these curved lines have nothing to do with any real force. There's no real force curving.
That way it's easier to see the inward and outward directions at any particular place. But it's important to remember this is just a visual tool. Nothing is actually flowing in this picture.
Right. So again, so you show all these pictures of something flowing, and then you say nothing's actually flowing. You don't understand how you're talking to idiots, obviously, because that's who would watch this cartoon on purpose, of their own volition, except to do what I'm doing, which is to make fun of it. But anyway, you're supposed to be educating people. So you spend all this time showing all these moving arrows, and then you say, well, there's nothing really moving in those directions in terms of the forces. Nothing electrical or magnetic is doing that. Okay, that's just what a piece of matter will do if I put it in a location. But it has nothing to do. And it won't even be what something will do. Again, these lines don't actually represent where something will go. So again, let's try again. Well, these particular ones do. But I mean, the ones around a magnet don't represent directions at all.
There's no electromagnetic fluid. It's not a thing. We can interpret the other divergence equation.
So again, he just said, so there's no fluid, it's not a thing, it's not really a correct analogy. So why do you present it that way? Why did you just show it and explain it as a fluid, as if it was real? Why'd you do that? When you say, don't believe what I just told you.
In the same way, it says the divergence of the magnetic field at some point is always equal to 0. So unlike with electricity, there's no such thing as magnetic charge.
So again, of course there is. Obviously. It's the same thing. They're monopoles of magnetism. And that's what happens to atoms when they transmit electricity, as they go from being polarly plus charge to polarly minus charge. They go from high pressure to low pressure. I mean, it's the same thing. So this is the part of where Maxwell is just off the rails. Well, the whole idea of Maxwell, of making two different fields, the B field and the E field, was just a mistake. All right? Just as they made a mistake by starting off with permutivity and permeability bullshit. It's not the correct way to do it. It's not it doesn't get to the elemental roots. The elemental root, there is no two fields. There's no such thing as electric radiation, and then there's a different thing called magnetic radiation. The virtual photons that control both of those things are the same virtual photons. They're real photons. They just haven't figured out that the force is also polarized. There's two kinds of it. Reflective of electrons, reflective on protons.
In other words, there are no magnetic monopoles.
So again, it's just silly. So explain to me how an electron and a proton don't fit whatever the criteria would be for a monopole. How are they not behaving exactly like monopoles?
Magnetic poles, like north and south, always come in pairs.
So again, is an electron a pair? No. Is an electron always associated with a proton? Well, it sort of will have to be, inevitably, in an explicit sense. But yes, if they're far enough apart, you don't call it a dipole anymore.
Consider the magnetic field around this bar magnet. Using that same imaginary sphere, the divergence is how much the field points away. Since the divergence of the magnetic field is always 0, There is always just as much field pointed into the sphere as there is pointed out.
Yeah, well, there's just as much energy, coming out of one end as there is in the other end. There's just as much black energy as there is red energy, blue energy as there is red energy, is all that's really saying.
Out of it, no matter where we put that sphere. This becomes pretty obvious using the fluid analogy. Every streamline that goes into the sphere comes back out.
Well, and again, but so he's doing it again. He's basically saying, let's use this wrong analogy that doesn't really have anything to do with the reality, that there is nothing doing those kinds of movements. None of the forces are moving in curved paths. None of them are going this way and that way. No, they're radial forces, and all you're saying is when I average them, when I combine them, when I create a product, what's the orientation of the product? And that's it. So they're just telling you which way the magnet will flip. They're giving you the flipping orientation of a magnet.
That's all there is to divergence. The curl, on the other hand...
Oh, yeah, waste my time. This is nonsense.
Why does this keep happening? Curl is a different story. Your first instinct might be to imagine those closed fluid loops again. And that's certainly an example of a curl. But this flow has a curl too, without loops of any kind. That's because the curl isn't really about the field itself.
Yes, that's right. It's just about how the intensity changes with distance.
It's about what the field might cause. In this fluid example, say we draw a tiny imaginary circle somewhere on the screen.
Oh, God.
Oh, come on!
There's no boot too small to try to step on him with. Yeah, so.
Come on, man. If we imagine some kind of paddle attached to that circle, the difference in flow between the top and bottom will cause it to spin. So even though the field itself doesn't circulate, the things inside it will. Now let's get back to electromagnetism. Faraday's law
Is that what he's going to do?
Says the curl of the electric...
So again, it's just a flipping argument, and there's all different ways you can illustrate the fact that something has to turn to the orientation of what it's being affected by. So there's no way to analogize it except to analogize it with actual magnetism, because that's so elemental. I could say, look, imagine acid being sprayed at you and water being sprayed at you, and then they mix it from a different direction. And one side of you is shielded against acid, and one side of you is, dissolved by water. And obviously you would turn to try to maximize the fact that you want to get hit with as much acid where acid doesn't hurt you, and you want to get hit with as much water where water doesn't hurt you. So you're going to turn to that field. You're going to turn to put the shield where the bullets are coming from, and shoot where the enemy is, something like that.
Field at some point equals the negative change in the magnetic field at that same point.
So here's this relationship between the B field and the E field. Like I said, it's exactly the same thing. So of course there's an equal sign, because the two things are just different descriptions of the same thing, which is all a charge phenomenon. I mean, if you want to say something is the elemental part, you'd have to say, well, what's the elements? And the elements are the electron and the proton, and they're clearly elements of charge. So that's where you have to say that's the fundamental thing. So when people say it's an electric universe, well, that's wrong. And people say it's a magnetic universe, well, it's technically not right either. It's a charged universe. There's two forces, and there's two kinds of matter, and there's two kinds of interactions. I mean, it's just 2 + 2 + 2. It's that simple.
Say we draw a tiny imaginary circle again, and we notice a magnetic field passing through that circle. If that field is changing over time, Faraday's law tells us there must be an electric field that curls around the imaginary circle. The curl of that electric field will be opposite.
So there's no field of electricity. There's the phenomenon of the atoms changing their polarity. So there's a fat atom here and a thin atom here, right? And the two are next to each other. And what's going to happen is the fat atom pressure through the electron is going to be conveyed to the small one, and they're both going to equalize. So this one will be a little smaller, this one will get bigger, and they'll equalize. And that's what's happening with atoms. Atoms are just going from big to small, big to small. So when you have an alternating current, obviously the big to small thing is just happening, right? You know, they're just doing this all day long. And when you have a direct current, it's always, this end always gets fatter, this end is always, you know, reducing that to what would be the norm at the other end. So you have high pressure here, you have normal pressure at this other end. And it's just always going to keep pumping to that end in terms of it keeps getting bigger, but it gets smaller because it has somewhere to go. There's a smaller source. There's a place for the pressure to get out. But there's no fields moving in those directions. No fields move. The only thing that can move is the pressure, and the pressure is the little photon things, the virtual photons move from one atom into the other atom and expand it. Goes from the high pressure, more photons in this atom, less photons in this atom. They exchange basically more photons in here, less in here. That's it. And when they do that, they become charged in the sense that their profile from somebody looking at it is going to see the atom go from being more of a proton atom to more of an electron atom. So it's going to see the atom switching from proton strong, oh I can see the sun, to the earth moves in front of it, oh I don't see the sun. That kind of thing.
It, the change in the magnetic field. But remember, the curl isn't about the shape of the field, it's about what the field might cause.
Yes, exactly. That's the whole point. It's about the product, the implication, the consequence of what the energy is doing. What does the energy cause? Okay, you're not describing what the energy is doing, you're describing what it's causing. First you should describe what the energy is doing.
If our imaginary circle happens to be a metal ring, we'll get a circulating current. That result is what matters. So where was I again? Divergence of the electric field, divergence of the magnetic field, curl of the electric field.
So this is another part where they really fail. It's just that the idea of when you put something circular, the idea is what makes that significant is that, you know, when it's straight, the energy just shoots out and it all escapes. But if I curl it, the wire, then you know some portion of the energy is hitting the other wire all the time, and that one's reflecting it back to this wire. So it's like you have to think of the wire in terms of its magnetic component as being a mirror. And so if the mirror is just facing out and it just shoots, well, nothing's going to happen. But if I curl the mirror, then the mirror is going to reflect the energy back and forth, and there's going to be a lot more interactions, and interactions are energy. So that's how you measure the energy, is through the number of interactions. That's how pressure makes itself known, is by hitting something. So the more times I hit, the more pressure I create. And that's why you amplify the effect by curling the wire. You're just really saying, make the mirrors bend so they face each other, and now whatever's trapped between them will have a multiplied effect. It'll be trapped, and it'll keep on making pressure.
Alright, there's one equation left, the curl of the magnetic field. It's pretty obvious from the bar magnet example that the magnetic field curls.
So again, there's no field curling. There's no energy curling. The only thing that curls is the movement of an object through space. So if I'm moving across a dipole, here's plus, here's minus. Obviously, if I'm something moving across that field, this and a minus, I'm going to be, you know, pulled in towards the positive, and I'm going to be repelled by the negative. So that's not even complicated. So I'm a mirror here, and I'm no mirror here. So obviously, where there's no mirror, there's no reflections. Where there's a mirror, all of a sudden I start reflecting and I get pushed away. More interactions, less interactions with my surface.
But let's take a look at Ampere's law and see what it actually says. A curl in the magnetic field at some point can happen for one of two reasons: an electric current passing through that point, or a changing electric field at that point.
Right, so the same thing. The electric current obviously is a changing field in the sense that the atoms are going from being pressurized to depressurized. They're staying in one place and they're getting bigger and smaller, no matter whether it's DC or AC. That's what's happening. They're changing their pressure. See, this is where it gets tricky, right? Because obviously the pressure change moves through them so fast that you're not going to see this oscillating thing with DC current. But anyway, and that's why, let's not go into why it does. That's why you need AC for transformers to work. But anyway, so again, this connection between B and E fields, they're the same energy. It's just a different manifestation. So obviously, when I have a dipole field where I have an electron and a proton close together, obviously I'm going to have a thing that's going to have to react to both of those things. This one that's reflecting and the one that's not. The surface that's mirror, the surface that's not mirror. And I'm going to react completely different depending on whether or not I'm going to reflect the energy back to something that can reflect it back to me. If there's nothing to reflect it back to me, the energy is inconsequential. I'll never have, it can't affect me. The equal but opposite reaction can't do anything. But if there is something for it to reflect off of, then the equal but opposite reaction becomes another action.
It's the longest of the four equations, which is why I saved it for last. Don't panic. We can handle this. Say we've got...
I don't think there was really too much connection, was there, between the equations and these simulations? But anyway.
Got an electric current in a wire. If we draw our imaginary circle so electric current passes through it, Ampere's law says the magnetic field should curl around that circle. Now let's...
Yeah, so this is sort of the right-hand rule. Now, the reason there is a tendency to move in one direction versus the other direction, that is a clockwise positive, counterclockwise negative, however we want to describe it, just has to do with the atoms aren't, it's not like a clock face. So they do 1 and 11. They don't really do 12 o'clock. So they always have that bias that they always start at 1, not 12.
Say somewhere along this wire we've got a capacitor. It'll act like a gap in the circuit, which means no steady current, which means no field, unless that current is alternating.
So the two things have, when they're just sitting there, plenty of field, plenty of force, plenty of stuff is happening, but it's not polarized, so it doesn't mean anything. Okay, and so it's not until you polarize it, that is, you change the pressure of the atoms, that you change whether it's back to completely mixed or not. You start separating the poles, so to speak. If I put the red thing and the black thing right on top of each other, then I get red and black mixed, and I can't see anything except, whatever that brown. Yeah, I should use blue and red, and all I can see is purple. But if I separate them, then I start seeing red and blue, and I don't see purple as much. And the further I separate them, the less I see purple.
Alternating current, or AC, opens up a lot of possibilities for us. Since the current in the wires is changing on either side of the capacitor...
So they're not showing any polarity here. They're not showing it going red to white to red to white to red to white. They're not showing any of the... And the real key to the capacitor is the fact that it is doing this reflecting thing, and it's slow. It takes an actual amount of time for the changes to affect the surfaces, and that's basically part of the function of a capacitor, is to distort, to take the things and take them out of phase, kind of, to put it simply.
The electric field inside the capacitor is also changing. That changing electric field creates a curl in the magnetic field around our circle.
Right, so what does this say? See, this changing electric field creates a curl in the magnetic field. It's the same. There's only one field. There's only one energy. There's only one force. Well, see, I just said there's only one force, and I want you to make a distinction between the positive element of the force and the negative element of the force. There's red and blue force, and you can mix the two forces or you can segregate the two forces. So, and that's all this conversation is about. That's the only elemental function.
Just like the current does in the wire. This keeps the behavior of the magnetic field smooth across the entire picture. There's a curl in the magnetic field.
So you will not find capacitors producing any strong magnetic field. So again, this is just sort of horseshit. The field he's talking about is inside the atoms of the material, and it's not something it's radiating in any significant amount. So even the way he's describing this, he's almost describing this as like, you know, he's creating some sort of magnetism this way. You don't create magnetism with capacitors.
All along the circuit chain. So what's the best way to visualize Maxwell's equations? Using tiny imaginary shapes and a little imaginary fluid.
Right. So no, the best way is to always remember the forces are in straight lines, and that's what Maxwell drew with charge, and charge is where it all starts. It all starts with the phenomenon of the fundamental difference between electrons and protons. They're fundamental, elemental, completely opposite reactions to circumstances. That's the start. That's the first cause. If you want to say there's a first cause for magnetism and electricity, the first cause is there's a fundamental difference between a proton and an electron. And all you're really trying to figure out is what mechanism is making that fundamental difference. The mechanism as they describe it in conventional physics is called the virtual photon, but their virtual photon doesn't have any polarity. So obviously they have no way to explain why it pushes or why it pulls, because they can't explain, because they don't understand the difference between the force being directed, changed in its direction, and the force being reflected. And those are the only two events happening. There's either the force, the energy, the little bits of energy, the moons, or the asteroids, however you want to metaphor them. The asteroids, they all go out of the object. They reflect off the object in a perpendicular dimension, or they reflect back. They bounce off of it. So you could understand if I made the universe out of asteroids and planets, you could understand that if the asteroid hits and bounces, well, they could get caught between the moon and the earth, and you know, something like that, if they both are bouncing the asteroid. So I have two kinds of asteroids, right? And I have two kinds of things, Earth and moon, and I have asteroids that bounce off moons, and I have asteroids that bounce off Earth, and I have an equal amount of both. And you could sort of understand that Earth will reflect this, will bounce stuff a lot, and moons can bounce stuff a lot between moons. But Earth and moons could never bounce anything, because everything that's reflective to the Earth is not reflective to the moon. And that's how the proton and the electron work. Everything that reflects off an electron diverts through a proton, and everything that reflects off of a proton diverts. So they can never create reflections between them. They can never create high pressure. That's where it all starts. Whether you want to say that Maxwell had the kernel of it, and Faraday and those people, I mean, when they drew these straight line force, they got it, and somehow he emphasizes the product of that force instead of emphasizing, why don't just show Maxwell's drawings of charge? Charge is where it starts. So that's his fundamental mistake. He doesn't understand that charge is the element. Protons and electrons are the epitome, the whatever, the king of the mechanism. They own it completely, and it is what causes magnetic polarity. They're obviously the magnetic monopoles, protons and electrons. Obviously. It's so fucking obvious. Again, cite somebody, explain to me how they wouldn't fit the definition. If you made a definition for what a magnetic monopole would look like, show me how it's not an electron or a proton. Show me. It fits the definition completely.
Divergence tells us how much a field points toward or away from a point in space. For electric fields, that's caused by charges. For magnetic fields, it's always zero. So
again, you just said it's always zero when clearly there's polarity. So clearly it's just idiotic to say it's always zero. it's obviously not always zero. I mean, it's obviously distinctly different. The north side and the south side are distinctly different, and they're just trying to say, well, there's no effect of that distinct difference. Of course there is. Yes, there's the same amount of force, but segregation matters. Whether you're getting hit by all blue force or whether you're getting hit by all red force matters to a proton or an electron. I mean, it's just stupid.
You know, magnetic poles always come in pairs. Curl?
So again, they always come in pairs, which they don't. I mean, just so frickin' clearly. I can separate electrons from protons. I can do it.
Tells us which way something inside the field might spin or circulate. In electrodynamics, that means we'll probably get some kind of electric current. Just remember, those shapes are imaginary, and that fluid isn't really there.
Right, and also nothing curls. That's actual force. No virtual photon was curled or bent in this experiment. That's what they should say. There's no actual bending of any actual force vector. No virtual photon bent anywhere.
They're just tools to help us visualize the math.
Well, you're doing it badly because you don't understand it. So all you have to do to visualize it correctly is do what I've done on my website, and what I've done in these videos is just show you the magnet. It's all red at one end and it's all blue at the other end, and then you just recognize that the blue means it reflects off an electron, the red means it reflects off a proton, and I know what a reflection happens. If I put a reflection between two objects and the thing just keeps, I reflect the force back, you shoot the force back at me, I shoot it back at you, you shoot it back at me, I'm creating more interactions, and the interactions are always the same, and there's no loss of energy for every interaction. So I've increased the amount of energy by increasing the number of interactions. Proximity becomes everything.
So what do you think? Should I do more videos like this?
No, they're stupid, they're wrong, they're incorrect, they're not even correct to your own theory, they're not really describing Maxwell appropriately, because Maxwell did start with charge, frankly. Charge is where it starts, and it's just stupid to say there's no magnetic monopoles. I'm just saying there's clearly, obviously, you can't have magnetism without a bunch of little magnets combining to create a big magnet. So we don't see any magnetic effects where we could say, there's a monopole, because it just can't happen for us, because we can't see, we don't live in the elemental. But the elemental has monopoles.
Your thoughts in the comments. Also, maybe answer the poll that pops up over here somewhere. If you want to see the actual math of divergence and curl, there's a whole chapter in my ebook on vector calculus.
Yes, why don't you just show them Maxwell's drawings of charge? The lines of force caused by charge. And you'll see that there's just straight lines radiating from objects. Straight lines. That's what the virtual photon, if they're ever going to show you a virtual photon, why don't you draw some virtual photons? How are you going to draw them? As curved lines? Never. You're going to draw your virtual photons as a straight line force radiating from something. A proton and an electron usually are something that has a polar bias.
Big news though, it's a physical book now. What? I know.
Oh yes, too stupid.
Right? It's crazy. It makes it feel so much more real to me. It's available through lulu.com, which helped me keep the price reasonable. Links for
price for a book by an asshole. Are you going to do you do all this antics in your book?
both the ebook version and the physical version can be found in the doobly-doo. Thanks for liking and sharing this video.
I hated it. But there was no hate button. I hate this video. This just wasn't one of those, so I didn't bother.
Don't forget to subscribe if you'd like to keep up with us.
Yeah, right. I have to tell people who are going to understand curl and divergence, I have to tell them to subscribe because they're so fucking stupid.
Until next time, remember, it's okay to be a little crazy.
Whatever. Stupid, silly, queer. It's okay to be a little queer. Well, sure it is. If you don't mind having people look at you and go, hey, that guy's queer. Yeah. So it's okay to be anything if you really don't mind people going, hey, that guy's... If you don't mind that. See, I don't mind people saying, oh, that guy's got really attractive hair. Yeah. Anyway, yeah, I don't mind. Anyway, till next time. In touch.
Chaos Fever.
I think this is, yeah, he's just doing commercials, so fuck it. Ugh, I hate this crap. This crap. Popular fucking culture sucks. Anyway, so till the next time and such. I mean, it's just such an insult to science to think that, oh, I have to put my Barney the I mean, you know, this is like Einstein saying, oh, I have to put my Barney the dinosaur suit on. Well, maybe Einstein did some of that, frankly. So, you know, he's not a good example. But the idea that diligent scientists, you know, scientists like the Curies or something, saying, well, we're going to go to, you know, distill radium today. Let's put on our Barney the dinosaur suit, you know, and crack jokes. You know. Fuck. It just sucks. But I've already pointed that out. But some things need to be emphasized over and over. I mean, I have to keep explaining to you. 2 kinds of matter, electron, proton. 2 kinds of force, electron reflective, proton reflective. 2 kinds of interaction, change in direction or reflection. That's all. 2 plus 2 plus 2. Yeah, that's it. 6. Turns out to be an even number. Well, who knew? When I was a kid, I thought the whole universe had to be based on the number 3. So 3 plus 3 is 6. So it kind of works. Anyway, there are miraculous coincidences in all of this. You know, I've sort of relayed before this story, but when I was a kid, I actually saw, like every night when I went to bed, turn out the lights, my whole room would fill up with these little colored dots, like little styrofoam beads of color, and they would swirl in 3 dimensions and move, and I would sit there just fascinated watching it. And, you know, and I'd tell, hey, does this happen to you? And, you know, everybody else in my family, does this happen to you at night? You know, and all this stuff shows up and it starts moving around. You know, what are you talking about? You know, they'd say, no, I see some spots. Sometimes I press on my eye, I can see a spot, but I don't see any little dots. These were like precise little dots. So it is kind of ironic. But then you would say, it's not a coincidence, right? It's not a coincidence that I probably had a bias. It just happens to be the bias towards the right answer. But anyway. So I had a comfort with the idea of particles, just because they were my best friend for a few years. They started getting malicious later. That's when they went away after that. But yeah, they started to get threatening. I can't remember exactly how that happened, but I do remember there was this negative component that came into it, where, you know, they were trying to like get into me or something. They were getting aggressive, and so it wasn't all fun anymore. But it's just interesting, those transitions. I used to fly all the time in my dreams when I was a kid, you know, flying, and I just don't do it anymore. It's kind of I miss it. It was never, you know, it's like dreams. Dreams always kind of fuck with you. So I'd have these great flying dreams, right, flying over everything, but they always turned into falling dreams because I never landed very well. So, you know, that was the downside, is you had a nice flight, but there's no wheels on the plane or something, and so I never had a good landing. It was always rough. Anyway. Not necessary context, I don't think, but I throw it in for free bonus. Yeah, that's all. It's nice to get a little bit of free stuff with your stuff, your free stuff. It's nice to get some extra free stuff with your free stuff. All right, anyway, till the next time and such. I think it's nice, personally.